G'day, John here. Welcome to another PyProx tutorial, helping you understand the impact of uncertainty in data and simulation. In the next few minutes, I'm going to teach you how to use Monte Carlo quadrature to compute any statistic of a vector value function. This tutorial will build upon a previous video that showed you how to compute the mean of a scalar function or model. To make sure this video does stay short, I'll focus on how to compute the covariance of a model, but I'll give you all the tools you need to compute and analyze a Monte Carlo estimate of any statistic. In a previous video, I showed you how to compute the mean of a scalar function fm that maps a d-dimensional random variable to a scalar. In this setting, the mean of a function is also a scalar and is simply the sum of the function evaluated at n samples divided by n. Similarly, the variance of a function is a scalar and is given by the last formula on the slide. But we can also use Monte Carlo to estimate statistics of vector value functions that map a random variable z to an s-dimensional vector. For example, we may want to compute the mean mass loss from a glacier in 10 years and in 20 years. In this case, s would be equal to 2. The mean of a vector value function is given on the slide. I use the notation fm subscript 1 to denote the first output of the vector fm, subscript 2, the second output, and so on. This means that the mean is now a vector, and we estimate it by summing each element of the output vector f at n samples and dividing element-wise by n. In contrast, the variance of a vector value function is a matrix and can be computed using the last equation on the slide. We can also estimate k statistics of a vector value function. I'll call estimators computing multiple statistics of vector value functions multi-output estimators. Multi-output estimators compute a vector of statistics. For example, when computing the mean and covariance of a model, we concatenate the mean with the flattened form of the covariance matrix. In these videos, I flatten the matrix by concatenating each row of the matrix to form a single vector of length s squared. You can see the form of the flattened covariance matrix on the bottom of the slide. Consequently, a multi-output estimator of a mean and covariance computes a statistic vector of length s plus s squared. To build multi-output estimators using a single model, we follow the same three-step procedure that I reviewed in a previous tutorial. Specifically, we randomly generate a set of samples of the input z, we then evaluate the model at these samples, and then compute the desired statistics by summing over the evaluations using the desired formula. Just like the scalar case, the mean squared error of a multi-output estimator is the best way to measure the quality of a Monte Carlo estimator of a vector value function. I'll leave it as an exercise for the viewer, but again, like the scalar case, the mean squared error can be decomposed into two terms. The first term is a squared bias and reflects how close the estimator gets to the true value q on average. The second term is the estimated variance and quantifies variability in the value as an estimator each time it's computed with a different set of samples, zn. However, unlike the scalar case, the mean squared error of multi-output estimators is a matrix. Computing the bias is straightforward, so in the next few slides I'll focus solely on how to compute the estimated covariance. To avoid as much confusion as possible, I'll refer to the covariance term in the mean squared error as the estimated covariance and the covariance between model outputs as the model covariance. In the next few slides I'll show you how to compute estimated covariances when estimating a vector valued mean, a flattened covariance matrix, and both simultaneously. However, as go, I'll introduce expressions that are more general than needed for this tutorial because they'll be useful for a later tutorial when I compute multi-output estimators using multi-fidelity estimators, which use multiple models. Let's start with vector valued mean estimators. In this case, the estimated covariance of two estimators that use evaluations of model m and n on the sets zm and zn is given by the expression on the slide. It is simply the model covariance multiplied by the number of samples in both the sample sets zm and zn divided by the size of those sets. If the function computes two outputs, that is s equals 2, then the model covariance will be a 2 by 2 matrix. The expressions for the estimated covariance of a flattened covariance matrix is more involved. It is the weighted sum of two matrices Vmn and Wmn. These weights are dependent on the size of the set Zm and Zn and their intersection. The exact form of Vmn and Wmn are shown on the bottom of the slide. The cross inside the circle represents the Kronecker product. A matrix raised to the crossed circle times 2 is the Kronecker product of the matrix with itself, and the small circle represents the element-wise Hadamard product. It can be a little confusing at first trying to understand these matrices, so on this slide, I expanded them a little for you. And on this slide, I expanded them further. I'm not going to spend any more time on these formulas, as you really just have to pass them in your own time. I just wanted to include them here so you can pause the video to look them up later. On this slide, I present the estimated covariance of a multi-output estimator, both the mean and flattened covariance. The estimated covariance is a 2 by 2 block matrix. I've already shown you the expressions for the diagonal blocks. The expression for the off-diagonal block is shown on the bottom of the slide. And on this slide, I expand the form of B slightly to hopefully help you if you ever want to understand the matrix B more completely. So that brings me to the end of another PyPox tutorial. Hopefully you now understand how to construct Monte Carlo estimators to approximate multiple statistics of vector-valued functions. Like for Monte Carlo estimators of a single statistic, the mean squared error is the best way to quantify the quality of multi-output estimators. However, the mean squared error of multi-output estimators is in general a matrix. See you next time.